Welcome to solverfy.
First, we are going to find the radius r, which is given by mv over qb, and this equation comes from the Newton's law, which is net force is equal to mass times acceleration. And in the case where the path is traveling along a circle or semicircle due to the magnetic field, this is equal to, so force is given by q times b, because sine phi is 1 here. This is equal to the centripetal force, so mass times the centripetal acceleration, which is v square over r, and this gives r to be equal to mv over qb, the equation that we are using here. So use this equation and we get this value of r, or radius, to be 5.14 meter. Now for the second part, if you see figure 27.81 from the textbook, the distance along the curve, or small d, is given by capital R times theta. So this is the d, small d is basically the arc, and that is given by the radius times the angle that the arc subtends at the center of the circle. So this gives theta to be equal to 0.25 over 5.14 meter, and theta is nearly equal to sine theta for small angle measurement, which is the case over here, and this gives sine theta to be equal to 0.25 meter over 5.14 meter, and this gives theta to be 2.79 degree, or in radians this will be, okay, I think it, so theta is basically not small, really small here. Okay, no, the theta is small, so let's go back to what we did. Yes, and in radians this is equal to 0.0486 radians. And since the velocity is constant here, the time will be given by uh, distance over the velocity, and we get this distance, we get the time to be 1.72 times 10 to the power minus 6 seconds. For the third part, we have to find delta x1, and that is given by, so delta x1 is the horizontal deflection at the point of exit from the field, and so to find that, we have to multiply d with tan theta over 2, and this is, and we use the theta from here, and we get this value of delta x1 to be equal to 6.08 times 10 to the power minus 3 meter. For the last part, we have to find delta x, which is delta x1 plus delta x2, and delta x2 is the horizontal displacement of the particle from where it exits the field region to where it hits the wall. And delta x2 should be given by capital D times tan theta, and we get this value to be 0.0244 meter, and we use the value that we found here and here over this, on this equation, and we get delta x to be equal to 0.305 meter. Now one thing to notice over here is d, small d, is much less than capital R. So the horizontal deflection of the particle is much smaller than the distance it travels in the y direction.